Übertragung via YouTube. Muy bien. Entonces, welcome everyone to our weekly colloquium of the Physics Institute of the UNAM in Cuernavaca, in Mexico. Our guest today is Dr. Vicent Romero-García from the Université se me olvidó, Le Mans in Francia. Yes. And let me say some few words on his vitae. So Dr. Romero-García did his PhD in 2010 at the University of Valencia in Spain. And his thesis was awarded with the Extraordinary Prize with European mention. And he did then 2 postdocs at the University of Valencia and at the University of Le Mans in Francia, where he is since 2014 CNRS researcher. He is member of the editorial board of the New Journal of Physics and the journal Acoustics, and principal investigator of several research projects. His research interest is transversal and lies in the frontiers between different topics as metamaterials, crystalline structures, acoustic materials, and disordered systems. Dr. Garcia's interest is focused on the wave propagation in complex media, paying special attention to several wave phenomena as perfect absorption, diffusion of waves, transparency, cloaking, bandgap engineering, wave guiding, filtering, surface waves, and diffraction, among others. Vicent, thank you very much for joining us today, at least virtually. Thank you for working late night for us. I think in France it's already 8 p.m. And we're looking forward to your talk.
Thank you very much, Thomas, for the nice introduction. And first of all, I would like to thank all the organizers for inviting me to participate in this nice colloquium, and to give me the opportunity to present the works that we have developed in the last years in Le Mans University. And today I would like to talk about control of the acoustic waves in sub-wavelength regime, so using metamaterials for perfect absorption and metadiffusers. This has been a long work with a lot of collaborators, as you can see in the slide. So we have been working in collaboration with several universities around Europe. And this has been the work that I have been developing in Le Mans University during the last, let's say, 6 or 7 years. With very strongly collaboration with my colleagues in the lab, Jean-Philippe Groby and Vincent Pagnot. So we have been working on that during this period. So let me start with a short introduction of my lab. So I belong to the acoustics laboratory of Le Mans University, which is a laboratory based in France. We have 4 sites. 3 that are in Le Mans, that you can see here in the map of France. We are here. And we have another site which is in Angers, which is the SEO. And basically, I'm in this building here, which is in the campus of Le Mans University. And the acoustics laboratory of Le Mans University is a joint unit between the National Center of Scientific Research in France and Le Mans University. It has been created in 1980, and as you can see here graphically, now in 2021 we have almost doubled the number of people working at the beginning of the creation of the lab. So now we are 170 people working in the lab. We have 70 faculty members, 11 that are CNRS. I'm one of these CNRS. We have 20 technical staff, 60 PhD students, and 2 important characteristics of our lab is that we have a common budget and we have a shared equipment. So all the people in the lab can beneficiate of the budget and the equipment. So the activities of the lab are divided in 3 main teams. as I will discuss later. So we have three teams, one that is transducers, the other one that is materials, and the third one that is guide and destructors. And the research that are developed in these three teams are based on acoustics. As you can see here in the slide, you can see several pictures in which I have summarized a little bit the different activities that we have that we developed at the laboratory, all of them based on acoustics. So we start with musical acoustics, and today we will talk about acoustic and elastic metamaterials, which is the topic in which I'm working nowadays in the lab. So the three teams that we have in the lab are transducers, materials, and guide and destructors. We have different activities that are devoted to each team. And in particular, we have some transversal axes, one that is based on non-destructive control, and the other one that is based on metamaterials. And I'm the leader of this transversal axis based on metamaterials that makes people work between different teams based on the topic of metamaterials. So this is the few words that I would like to say about my lab in France. So I will start now my presentation. So today, I have divided my presentation in four main parts. The first one, that is an introduction in order to see why we want to work with metamaterials to create perfect absorbers or metadiffusers. Then a second part in which we will talk about the possibility to create perfect absorbers in the reflection problem. The third part is based on the transmission problems, so in ventilated problems, and how we can obtain perfect absorption. What are the several possibilities that we can develop to obtain this perfect absorption. And the fourth part is devoted to the topic of metadiffusers. So how we can use metamaterials to control the diffusion of waves, in particular the diffusion of sound. So in acoustics, as probably you know, we have two main research lines, one that is based on absorption of waves, and the other one which is based on the control of diffusion of sound. So when I'm talking today about acoustics, we talk about audible acoustics. So these two topics has the main problems at low frequencies. So it's very difficult to absorb waves at low frequencies with a small amount of material, and the same for the diffusion of waves. So today, I would like to discuss two questions. The first one is if we can find sub-wavelength structures based on metamaterials to improve the behavior of the existing systems for absorption and diffusion, and how we can control the absorption of sound efficiently at low frequencies by using metamaterials. So to do that, we will use different ingredients. The first one is the low frequency, the resonances. So let's consider that we have here a quarter wavelength resonator, so a tube open from one of the two sides. And we know that the resonant frequency can be expressed by the sound velocity inside the tube divided by 4 times the length. So if we want to shift down the resonant frequency of this quarter wavelength resonator, we have one possibility, that is we increase the length of the quarter wavelength resonator. And this is what the Chinese group published in these physical review letters. So they create the coiling up materials in which the length is created by this labyrinthic path. So with a given length, in fact, the effective length is much, much larger than the one that we have. So we can shift down the resonant frequency of this quarter wavelength resonator. But the other possibility is to use what we call the slow sound. So we can introduce dispersion inside of this material by, for example, loading resonators. And then here, sound velocity depends on frequency, and we can reduce the sound speed inside the material in order to reduce the frequency of the resonance of the system. So we will use this slow sound. So here, what we can do is that the second ingredient is that we need to tune the losses in order to increase the impedance mismatch, because the second problem that we have to solve at low frequencies to obtain, for example, perfect absorption, is the creation of good material with impedance match conditions. And we can do that by controlling the losses. And in fact, in the region in which we have a slow sound, as you can see here, for example, in a periodic material loaded with Helmholtz resonator, here you have the region with a slow sound that we will see later. In this region, in fact, we can control the losses by tuning the geometry of the system, as I will explain later. So with these two materials, with these two properties, we can create metamaterials that are basically here locally resonant materials in order to introduce a strong dispersion and control the impedance mismatch by using the viscothermal losses. So the two arrangements, or the two materials that I will discuss today, are shown here in this slide. The first one, you can see that here you have a wall in which you have several slits here, in which the slits are loaded by what we call Helmholtz resonators. And these slits can be opened by the two sides of the material. So in that case, you will have an incident wave and then one wave that will be reflected and the other one transmitted through the slit. And the second problem will be the same material in which behind of them there is a rigid wall, and then we only have the reflection of waves due to the presence of this rigid wall. So in these systems, the losses are accounted in the slits and also in the Helmholtz resonators. So the losses are the viscothermal losses due to friction of sound with walls. And also we take into account the correction length of the Helmholtz resonators and the slits in order to consider the effects of the higher order modes in the system. So let me start just by discussing the dispersion relation of an slit loaded by Helmholtz resonator. Consider that you have this slit that is infinite in the x2 direction. You have a unit cell that is made of a Helmholtz resonator with a length A here. And then you can calculate the dispersion relation by imposing the Floquet-Bloch periodic boundary conditions. So here in blue lines, you have the dispersion relation for the case in which losses are not considered. So here you can see that at the resonant frequency of the Helmholtz resonator, which is for this case at around 500 Hertz, you create a band gap here. I'm representing here the real part of the wave number in terms of frequency. So you can see that from 500 Hertz, the wave number is, the real part is completely zero, and the imaginary part is quite big, meaning that in fact, wave propagation in this range of frequencies is forbidden because we create a band gap. More interestingly, just before this band gap, we have a really strong dispersion because here, in fact, we don't have a linear dispersion relation. So this means that the sound velocity or the sound velocity depends on frequency. So you are strongly dispersive. And in particular, you can see that if in the red line, we consider now the presence of the losses. So we calculate the dispersion relation considering the losses. And here you can see that before the starting of the bandgap around 500 Hz, we have a region in which we have a strong dispersion due to the losses, but also a strong part here of the imaginary part that will introduce losses in the system. So we can use this region in order to create our absorbers. So let me analyze now the sound velocity inside of this periodic material. So I will analyze the derivative of this, this dispersion relation, the real part. And here you can see that in fact, the sound velocity here is divided by almost 5 times the sound speed of air. The sound speed of air is 340 meters per second. And here, in fact, what we have is that the sound velocity is really slowed down. So it's very slow with respect to the real sound velocity in the slit. So here you can see an animation in which you can see that the wave arrives from one side to this slit with the Helmholtz resonator, and then inside the slit, the propagation is really slowed down because of this effect of slowdown due to the presence of the Helmholtz resonator and the strong dispersion that they have introduced in the medium. So in fact, if you think about this material here, this is nothing else than a Fabry-Perot resonator, in which the resonances are C divided by 2 times the length of the material. The thing here is that as the sound velocity is strongly reduced, the resonant frequency of this material is also strongly reduced. So this material behaves like a deep sub-wavelength material because of this slow sound. So we will use this property in order to create deep sub-wavelength absorbers. And let me discuss first of all the general problem of 1D reciprocal scattering. So let's consider that we have a resonator at the position x equal to 0. So the resonator is called here sigma here. This resonator is excited by 2 waves, A with amplitude A and amplitude B here. And this resonator reflects these waves with amplitudes D and C. So we can relate the incoming and the outgoing waves by means of the well-known scattering matrix here. And in the most general case of a reciprocal scattering problem, this scattering matrix can be a asymmetric matrix in such a way that the reflection from one side of the resonator can be different from the reflection from the other side of the resonator. So if now we take this scattering matrix and we evaluate the eigenvalues, these eigenvalues are frequency-dependent functions, and they depend on the reflection and transmission coefficients of the resonator that we are dealing with. And these 2 eigenvalues has associated 2 eigenvectors of the system. So if we analyze what's happening when we have a eigenvalue that is equal to 0, then this corresponds to the case in which the outgoing amplitudes, so C and in this case, in this plot D, are exactly 0. And this means that perfect absorption can appear when the the good eigenvector is used to excite the system. So importantly, in the lossless case, we have one property of the scattering matrix that represents the temporal invariance. And this is that the complex conjugate of the scattering matrix is equal to the inverse of the scattering matrix evaluated at a complex conjugate frequency. So let me keep in mind this relation because I will use it later in order to explain some properties. So this eigenvector, this eigenvalue equal to 0 appears at the frequency at which the transmission coefficient and the reflection coefficients are related with these two properties. Okay, and when the incident wave corresponds to the real eigenvector associated to this eigenvalue. So now that we know the conditions that we have to obtain to create this perfect absorption, which is that the eigenvalues of the scattering matrix must be 0, let's analyze three different cases. The first one is the reflection problem. So let's consider that we don't have the right-hand side in this scheme here. And so in that case, we have the incident and the reflected waves only that are created by this resonator. And then the scattering matrix is nothing else than the reflection coefficient. And the reflection coefficient, in fact, if we want to obtain perfect absorption, should be equal to 0. So the reflection coefficient is also what we called previously the eigenvalue, even if now is an scalar in this particular problem. So we will start discussing this simple problem of the reflection in order to see what we have to do to have perfect absorption at low frequencies. The second problem is the asymmetric resonator. So let's consider that we have the full problem with the transmission, but in that case, that sigma is asymmetric in terms of reflection. So we have that the reflection coefficients are different from both sides. And then we have to analyze what are the conditions to have perfect absorption. And this happens when you have these conditions. And as we will see, the only possibility is that one of the reflection coefficient must be 0, and then the transmission coefficient will be also 0. And this case is the asymmetric resonator that will produce unidirectional perfect absorption. If we want to have a symmetric resonator here, in which the reflection is the same from both sides, the only possibility to have perfect absorption is that the transmission and the reflection must be equal depending on plus and minus. And in fact, to have perfect absorption, both should be equal to 0. And we will see that this is a, let's say, relatively complicated problem because we have to subdivide this problem in two sub-problems. And we will see that to have perfect absorption in these symmetric resonators, we will need degenerate resonators. So let me start by discussing the reflection problem. So let's consider a very simple case. We have a wall in which we have a quarter wavelength resonator here. And at the end of the quarter wavelength resonator, we have an admittance Y0 that can introduce losses in the system. In these slides, I will use the temporal convention minus I omega t. I will consider in that case that we are in the low frequency approximation, so considering that we have plane waves. And in that case, the pressure at one particular point can be expressed by the combination of the incident and the reflected waves. And this reflection coefficient accomplishes this relation with related to the temporal invariance of the system, as I previously discussed. And in fact, we can evaluate this reflection coefficient for this particular problem because we know the expression of this reflection coefficient here. And we can see from this relationship here that at a given frequency for which the reflection coefficient presents 0, there is a complex conjugate frequency for which there is a pole of the reflection coefficient. And here I represent this reflection coefficient here in absence of losses. So here I don't have this admittance. So here I have just a rigid wall. So I have a Newman boundary condition. And we can solve this problem by using, for example, the transfer matrix method is very useful to solve that. And around the resonant frequency of this quarter wavelength resonator, we can obtain two expressions for the pole and the 0. So here in the map, I plot in fact, I plot the absolute value in logarithm scale of the reflection coefficient. And you can see that we have at a given complex frequency here shown with a green dot, we have the 0. And at the complex conjugate frequency, we have the pole of the reflection coefficient. And in fact, in the real frequency axis, which is the physical frequency that we will measure in an experiment, here we will have that the reflection coefficient is equal to 1 for all frequencies, because in that case, I'm in the lossless case. What happens if now we introduce losses in that system? So if we introduce this admittance in this system, in fact, the expression of the reflection coefficient can be modified, and the expressions of the pole and the 0 are also modified, introducing an imaginary part here that depends on the admittance that we are introducing at the end of the tube. And you can see that, in fact, as soon as you introduce these losses, you can move the pole and the 0. In particular, you move the 0 through the real frequency axis. And there is a particular configuration in which the 0 of the reflection coefficient is in the real frequency axis. So if the reflection coefficient is 0 in the real frequency axis, then you obtain the absorption, which is perfect. You obtain perfect absorption at this particular configuration. So this condition in which the losses that you have introduced in the system compensates this distance, that is the leakage, in the lossless case, this corresponds to the critical coupling condition or to the impedance match condition. So we have to know what are the losses that we have to introduce in the system in order to create this perfect absorption. So now that we know what are the conditions that we have to obtain to create these perfect absorbers, we have designed two different systems. The first one is this one, which is just an array of Helmholtz resonators that are loaded in a small slit here, placed in front of a rigid wall. And then we have designed the geometry of these Helmholtz resonators in order to have the good amount of losses that compensates the leakage in order to create these critical coupling conditions or the impedance match condition. And here you can see the plot of the absorption coefficients in terms of the frequency. And you can see here in different lines, here you have the circles that are numerics, the crosses that are experiments, and the red and blue lines that corresponds to the analytic results via the transfer matrix and via the effective parameters of the system. And you can see that at the design frequency, which is around 330 Hertz here, more or less, you have the perfect absorption as designed by our experiment. So here you have a picture of the panel that we have introduced in our square impedance tube. And here you can see that we obtain perfect absorption with a material that is 88 times smaller than the wavelength that we are working. Here you have the parametric analysis with all the different geometric parameters, and you can see that as soon as you change one of the different parameters, you can always obtain the same configuration at which the 0, which is this blue dot, arrives to this real frequency axis. So the other configuration that we have developed in collaboration with Antonio Fernández Marín, who is here in the audience and now is in the Departamento de Ciencias Básicas del Tecnológico Nacional de México, en el Instituto Tecnológico de TU-ACAN. We have developed this system in which we have the slit, and the slit is loaded with a resonator that is made of an aerogel plate in front of a cavity. And in fact, this system has been modeled by using the transfer matrix method and also numerical simulations. And we have adapted the cavity and the losses introduced in the slit in order to work at the resonant frequency close to the aerogel plate that is introduced here, in order to create this perfect absorption that can you see here at around more or less 600 Hertz. And here this system is 13 times smaller than the wavelength that we are developing. So here you have the numerics and the analytics together with the experiments, and you can see the good agreement at the resonant frequency. So these two systems has been used to prove and to develop different techniques. So this one with the Helmholtz resonators has been used to see and to analyze the quasi-unidirectional absorption. So we have studied the absorption capabilities of this system at the resonant frequency for different angles of incidences. And you can see that, in fact, the perfect absorption here for different angles is maintained, is kept up to up to almost 60 degrees of incidence, meaning that if you evaluate the performance of these systems in diffuse field, you have an absorption that is almost 95% at the resonant frequencies in the diffuse field. And the work with the aerogel plane allowed us to develop a technique based on the Argon diagram. So we represent the reflection coefficient in the complex plane here. We represent the real and the imaginary part. So here, each point of the black dotted line represents a frequency of the reflection coefficient in the lossless case. So in the lossless case, we have a unitary circle here that represents the reflection coefficient in the complex plane. And as soon as you introduce losses, the circumferences changes the radius. And for the case in which we have the perfect absorption, the circumference is tangent to the origin of coordinates. So here you can see the results for the developed material, and you can see the transfer matrix and the finite element methods being completely tangent to the origin. And here you have the experiments that presents this kind of Argon diagram that are very close to the origin. So we will use these Argon diagrams to develop several things in this work. So now let me go to the case with perfect absorption for the transmission problem. In that case, I will talk about the two cases. The first, the mirror asymmetric resonator. So here you can see an example of mirror asymmetric resonators. Here you can see that you have a wall with two different Helmholtz resonators at two different slits. So you can imagine that if you evaluate the reflection coefficient from one side and the other, the reflection coefficient will be different. And then the transmission coefficient, as we consider the problem reciprocal, will be the same. So again, here, losses are accounted by means of the complex and frequency dependent density and bulk modulus and length corrections also. So let's analyze this case step by step. So here, in order to have perfect absorption, we have to, in fact, remove transmission and reflection. So one way to do it is, okay, let's consider a resonator here that is placed at frequency F1. And at frequency F1, the transmission is 0 in the lossless case, and in the lossy case is almost 0. It can be very, very, very small. And as soon as you have this frequency, in fact, this resonator acts as a wall for the second resonator, and then we have to apply the same arguments that we have used for the previous discussion of the reflection problem. So we introduce a second resonator that introduces the good amount of losses to present a perfect absorption or quasi-perfect absorption between the frequency F1 and F2, as you can see here on the slide. So here you can see the analytic experiment and numerics showing the perfect absorption at one particular frequency. Here you can see the annulation of the reflection and transmission. However, the pay that we have, the price that we have to pay in order to remove, to have perfect absorption from one side is that from the other side, of course, the system is not impedance match and we don't have perfect absorption. However, here, as soon as you have understood what's happening with this system, you can say, okay, I can add a third resonator and create a second peak of absorption. So here we have two resonators in which the two zeros of the eigenvalues of the scattering matrix are in the real frequency axis, creating this perfect absorption at this particular frequency. Then we introduce a third one, and we design other frequency here that creates perfect absorption. So we introduce a second pole here, a second zero that creates this second resonant frequency, and we can do that step by step. For example, here I show you an example with 9 resonators that creates 8 peaks of perfect absorption with 8 peaks, 8 zeros that are placed in the real frequency axis for the two eigenvalues of the scattering matrix. And then what you have to do is, okay, now instead of asking to the system to be perfect absorption at particular discrete frequencies, you optimize the system by doing an integral between a range of frequencies, and then it introduced a 9th zero, and you can see that in fact even if the absorption is very, very flat in the range of frequencies of interest between 400 and 1000 Hertz, even if the absorption is flat, the zeros are not at all in the real frequency axis. So that means that this plateau is not a plateau of perfect absorption, but the small quality factor of the resonators that we are working with produces that, in fact, in all the range of frequencies, we have a very flat perfect absorption. So we have used this in order to develop this kind of system here. You can see here you have 9 resonators placed in cascade here inside this cavity that reduces the heat of the cavity. And here you can see that we can create perfect absorption or a quasi-perfect absorption between 300 and 1000 Hertz with a material that is 11.3 centimeters, so meaning that the system is bigger than 10 times is smaller than 10 times the wavelength. So it's quite effective in terms of absorption for low frequency sound. So now let me discuss the mirror symmetric problem. The mirror symmetric problem consists in the case in which we have a material that is symmetric with respect to the middle, and in that case the scattering matrix is symmetric, being the reflection coefficient from the two sides equal. In that case, the eigenvalues and the eigenvectors can be written like that, but I would like to notice that in fact this full scattering problem can be divided in two subproblems. One that is symmetric, meaning that we introduce a Newman boundary condition in the middle of the system, and the other one that is antisymmetric, meaning that we have an antisymmetric boundary condition in the middle of the system. In that case, in the symmetric problem, in fact, you can see that we create a reflection problem in which the reflection coefficient is T plus R, where the transmission and reflection coefficients are the ones of the original problem. So you have that the reflection coefficient is one of the two eigenvalues of the scattering matrix. In the antisymmetric problem, in which we consider a Dirichlet boundary condition in the middle of the system, in fact, the reflection coefficient that we obtain is the reflection minus the transmission coefficient of the original problem, which is the other eigenvalue of the system, of the scattering matrix. So you can see that the reflection and the transmission and also the absorption coefficient of the full problem can be expressed as combinations of the reflection and of the reflection coefficient of the symmetric and antisymmetric problems. So look, if we regard the expression of the absorption coefficient here, you can see that to obtain perfect absorption, so alpha equal to 1 at a given frequency, we need to simultaneously obtain that the reflection coefficient of the symmetric problem and the reflection coefficient of the antisymmetric problem will be equal to 0. Meaning that if these two problems are 0, then the absorption is equal to 1. Let me show you a simple example here, which is an slit, which is a Fabry-Perot resonator, in order to discuss what are these conditions. If we study the reflection and transmission coefficient of this simple problem, you have the peaks of reflection and transmission at the resonances of the Fabry-Perot resonances. And at these particular resonances, we have an absorption coefficient here that, as you can see, is not bigger than 0.5. And why is not bigger than 0.5 is because if you look at the eigenvalues of the scattering matrix, in fact, the ones that correspond to the symmetric problems appears at one frequencies, and that these frequencies, we don't have nothing in the other eigenvalue, so in the antisymmetric problem. So this means that only half of the problem can be absorbed. So here, you can see that at this frequency, we have almost 0.5. At this frequency, we have almost 0.5. And here, only 0.5 can be obtained. In order to have perfect absorption, we will need to put the 0 of one eigenvalue at the same frequency of the 0 of the other eigenvalue. So how we can solve that? We can solve that by using the Degenerate Resonators. And to solve that, what we have developed during the last years is this kind of resonators. Here you have a resonator with two slits, one that presents two Helmholtz resonators, and the other one that presents one Helmholtz resonator. And in this case, with one Helmholtz resonator, in fact, we can only excite one symmetric resonance, meaning that it's symmetric with respect to the middle. In the second slit, with two Helmholtz resonators, we can excite the first and the second mode of these, let's say, Fabry-Perot resonators. So we can excite the symmetric and the antisymmetric modes of this Helmholtz resonator. So in that system, we can have symmetric and antisymmetric resonances at the same time. But to do that, we have to tune the geometry of the Helmholtz resonators in order to fix the resonance of the symmetric and the antisymmetric problems at the same resonances. So here in that problem, as previously, we have considered also the losses and the correction length of the Helmholtz resonators, but in order to consider the coupling between the different slits, we have to consider the blow modes in the exterior medium. So we have to consider the multimodal propagation outside the medium in order to consider the effect of the slits, because we have two slits by unit cells. So let's talk about the antisymmetric resonator. In that case, we use this antisymmetric resonator first because in that case, we can excite two, and the symmetric and antisymmetric, and the only one that has antisymmetric resonances is this antisymmetric resonator. So first we will tune the problem for the antisymmetric problem, and then we will tune the geometry for the symmetric problem. So here, when we consider that the pressure is equal to 0 in the middle plane of the system, so considering that we have a Dirichlet boundary condition, we can analyze the reflection problem, and we can solve, as we have previously done for the reflection problem at the beginning of the talk. We can just tune the viscothermal losses of this Helmholtz resonator by tuning the geometry in order to obtain perfect absorption at a given frequency. In this case, I use 800 Hz as tuned as the target frequency. So you can see that we can tune the losses of this part of the system in order to have perfect absorption in this anti-symmetric problem. So you can see here that only the lower part of the resonator is activated because the upper part here is not sensible to the anti-symmetric resonances, because here we can only obtain, we can only excite resonant symmetric resonators. So once we have tuned this part of the problem, this will be kept, and we won't change any of the geometry of this Helmholtz resonator, and we will consider that we have the Newman boundary condition at the middle of the system in order to tune the symmetric resonator. And in that case, we only play with the resonator in the symmetric part of the problem. So here you can see that at 800, we have perfect absorption here, as we fixed 800 to the target frequency. And you can see that, in fact, in that kind of problems, we excite the two resonators, because the two problems can excite symmetric resonances. So here we tune the resonator, taking into account the possible effects of this one that are constant in geometry because they have been already fixed here. So once we have impedance match the two sub-problems, so we have the geometry, we can 3D print the structures. Here you can see the building block that we have 3D print in France. So here you have the slit with the two Helmholtz resonator for the anti-symmetric problem, and the slit with the single resonator to the symmetric problem. And we can introduce this system inside our square impedance tube and measure the absorption in the transmission problem. And you can see here that, in fact, in red, you have the transmission coefficient. In blue, you have the reflection coefficient, and in black, you have the absorption coefficient. And you can see that at 800, we have this perfect absorption that is produced by using these two kinds of resonances. One that is symmetric, as you can see here. I'm plotting here the absolute value of the pressure field. So here you have a symmetric resonance, and here you can see an anti-symmetric resonance with a node in the middle. Here I plot the Argon diagram in order to see that effectively, when we consider losses, we have the circumference that is tangent to the origin of coordinates for the two eigenvalues of the scattering matrix. And this produces this perfect absorption. I would like to notice here that, in fact, all the simulations and all the numerics that we have and the analytics that we have considered here, they have been developed using the block waves. So we have considered the possible coupling between the slits here. If we only consider plane waves, in fact, the problem is not at all the same and is not well reproduced. So if we consider, for example, transfer matrix in order to analyze this kind of problems, the absorption coefficient and the reflection coefficient that we obtain is not at all the good one as we obtain in the experiments, because when we consider plane waves, we don't have the coupling between the two slits. So in that kind of systems, the coupling with the with the exterior medium and the slits is very, very, very important. So for this part, and I think I will stop here my presentation because I have been already talking 47 minutes. So we can stop here. So for this part, for the identical resonators, we can see that we can obtain perfect absorption in the case of reflection problem. And if we have identical resonators, in fact, we have seen that we cannot obtain perfect absorption in transmission problem. And to obtain this perfect absorption in transmission problems, we have to either use asymmetric resonators. So we have shown in this work a sub-wavelength asymmetric panel with perfect absorption at 300 Hz with a length that is 40 times smaller than the wavelength. So we have break the symmetry and we have imposed impedance match condition in order to obtain unidirectional perfect absorption. And this concept can be applied in cascade in order to create this rainbow trapping absorber, which perfectly absorbs waves from 300 Hz to 1000 Hz. And finally, I have shown the possibility to create perfect absorptions in symmetric problems, so mirror symmetric absorbers, by using degenerate resonators and impedance matching. But importantly, you have to consider here that the block waves in order to take into account the coupling between the slits, which is critical for this kind of designs. So I will stop here. And perhaps we talk in another opportunity about metadiffusers. So here I will only, I have only shown you the results about absorption. So thank you very much. If you have questions or you want to ask me about this kind of structures, feel free to ask, no problem. Thank you very much for your attention.
Thank you, Vicent. Thank you very much for the very nice, very interesting talk. Are there questions, comments from the audience? Maybe I start with one question. At the beginning, you mentioned briefly the effect of the shape of the resonators. My question is, there are other geometry factors. For example, this parameter, I think it was HA and HC, the height of these small tunnels. So how do your results change with all these geometry factors which you have? So do you optimize them or?
Yes. In fact, just I can go back to this. So here, for example, in fact, what we have in our case, in the acoustic problems, we consider that the system presents viscothermal losses. Okay? Viscothermal losses appears due to the fact that the sound has frictions with the walls, and the acoustic energy translates in heating the material, and then you have absorption, right? So this is strongly dependent on the geometry of the system. And in fact, what we have done here is that we have an analytical model that can calculate the reflection coefficient depending on the geometry of the system. And in fact, we optimize the reflection coefficient in order to minimize it as much as possible, just by playing with the geometry. Okay, because it's the crucial parameter here in order to increase or decrease the losses of the system. Okay, so for example, here you can see the sensibility of this perfect absorption peak with the different parameters.
I see.
That we have. So we have Ln, which is the length of the neck. You have H. So for example, let's take Ln is the yellow line here. Okay. So if you increase Ln, normally what you do is you decrease the resonant frequency of the resonator. So you can see that in fact the zero is moving along this line here, right? And at some particular position, the zero arrives to the real frequency axis. The same happens, for example, with the WC, which is the width of the cavity, right? So if you increase the volume of the cavity, you will decrease the resonant frequency of the Helmholtz resonator, and in fact, you will move the zero at lower frequencies. And at some particular configuration, you will have this perfect absorption, right? I see. What we need to work with all of these kind of structures is always an analytical model that depends on the geometry, that takes into account the viscothermal losses, and then we have to be able to evaluate the reflection and transmission. As soon as we have that, we can create an optimization problem that optimizes the geometry to have a perfect absorption at a given frequency. And this corresponds to the case in which, in fact, you compensate the losses with the leakage of the system, and this very nice theory with the scattering matrix and the eigenvalues and eigenvectors.
I see. Thank you very much for this very clear answer. I have another question. When you showed these two resonators in series with these two resonance frequencies, maybe you can show again this one before, I think. I see. Yes, this one. Yeah, this one. There are these peaks at F1 and F2. They have different heights. So at F1 you have only about 50% absorption, and at F2 you get almost perfect. You get perfect absorption. So what is the reason why is F1? Because later you showed this series of 8 or 9 resonators, and they were absorbing perfectly within certain frequency range.
Yeah, thank you very much for this comment. In fact, look, there is an important thing here, because here you have one resonator that is working at frequency F1. Right? And this resonator at frequency F1 has a transmission that is very, very small, right? So at this frequency, this resonate or close to this frequency, and for frequencies, in that case, higher than F1, you have a band gap because the slit is very small here, right? So from frequencies bigger than F1, the transmission is very small, right? So you can see here, for example, if you evaluate the transmission, you have that here you have a small transmission, but from F1 you have nothing that is transmitted, right?
Yeah.
So from this frequency F1, this resonator acts like a wall.
I see.
And then we add a second resonator with a frequency that is higher than the frequency F1, right? And in fact, we create a perfect absorption that is between these two frequencies. It's not at F1, neither at F2. It's always between the two.
I see.
Because we cannot put this at the same frequencies. So here, between the two, we create this perfect absorption, right? And if you go to the cascade process, I cannot zoom here, but in fact, the perfect absorption that we obtain, the peak, is not at the frequency that we create here.
I see,
It's always a little bit before this frequency.
I see. Thank you for clarifying this question. A question regarding with your next transparency. What are the limitations to extend this frequency range? So you get their perfect absorption from between 400 and let's say 1000 hertz. So can you make this frequency range even larger, broader? Okay,
it depends on the number of resonators that you can put. The bigger the number of resonator, the larger the broadband frequency range you can obtain. So in fact, everything is related to the number of resonators here. In that case, here in that problem, we use 8. In this particular problem, we use 8 resonators. So we have 7 frequency peaks. So it's that. But yes, it depends on the number of Helmholtz resonators, and in fact, the frequency range is always limited between the smallest frequency and the highest frequency of the resonator. Sure. So here, in this example, for example, you can see that we change the cavities in the Helmholtz resonator.
I see.
So in fact, here you have the higher frequency, and here you have the lower frequency. And in fact, you produce this absorption at different positions on the system at different frequencies. So this is why these kind of systems are called rainbow trapping, because you are creating like a rainbow inside the system with perfect absorption.
Okay. So this system has a size of about 11.3 centimeters, right?
Yes.
So which material do you use there for the 3D printing?
This is 3D printed in an stereolithography system, 3D printing system, and it's like a plastic that is called Acura. But it's the properties is like a plastic. In fact, for acoustics, what we need is that the material presents at the end of the impression presents an impedance that is much bigger than that of the air, and in particular that the material do not present porosity. Because if you 3D print these materials with PLA, for example, with the position of filaments, then at the end of the 3D printing, you will have something that is porous, and you will have something that presents also rugosity. This will change the losses in the system. And in fact, we have already tried to do that kind of things with the position of filaments. And we always have some problems because they are not close to our analytical models due to the fact of these rugosities and these porosities. So it's like this is like a plastic with rigid walls and not without rugosity.
I see. Thank you very much. Okay, are there further questions, comments from the audience? Yeah, Luis Mochan. Luis, you raised your hand. Go ahead, please.
Yes. So just to be clear, the mechanical properties of the walls of these resonators are irrelevant. You take them as completely rigid. Is that correct?
Is that correct? Is
okay.
the walls of the Helmholtz resonators and the system that we have analyzed here are considered rigid, so Neumann boundary conditions. I have to say that, for example, that kind of systems have been numerically evaluated with considering the mechanical properties of the walls, and there is not too much effect in the absorption coefficient. In fact, you can see the good agreement between the experiments and the analytics numerics, considering that the walls are rigid. So the approximation can be considered very good. And in fact, in time of computation time is very, in fact, you gain a lot, because if you have to consider the mechanical properties of the walls, then the numerical calculations takes a lot. And if you want to do optimizations, it's complicated.
Do you know if there is some kind of analogy in the electromagnetic case of these Helmholtz resonators?
Yes,
some system that is inert, but that has a sub-wavelength absorption or resonance?
Yes, in the electromagnetism, they used, for example, split ring resonators of this kind of things, and they have used several. In fact, there are several papers that in fact they do the similar things that we have developed here for acoustic, and in fact we are motivated and really motivated by this kind of works. For example, if you look at the works of Fan or Yarif on that kind of systems, in fact the critical Camping conditions comes from the electromagnetism. So yes, you can find several systems that can work as perfect absorbers. In particular, you can find works that uses these split ring resonators.
Okay, thank you very much.
Thank you very much.
Okay, are there further questions, comments? If this is not the case, Vicent, thank you very much again for joining us today. Hope to see you at some point here in person in Mexico, in Cuernavaca. And yes.
Thank you very much for your attention, and thank you very much for inviting me to this colloquium. If the situation changes and everything goes better, it will be my pleasure to visit you in Mexico. So, and in fact, the same for you. If you want to visit us here in Le Mans, in France, you are more than welcome. We can try to find some research lines that can be joined with the two laboratories. I think that thinking in wave physics in general, we can find very nice topics to collaborate. So if you want to come to here to France, you will be more than welcome.
Okay, thank you very much, Vicent. Thank you very much.